Okay, so let me go over, let's just go over homogeneous linear equations. The We're gonna start from the spring mass system, my dou prime plus gamma y prime plus k times y is equal to f. Yeah, we assume that all of the constants of property, I mean mass and gamma and k, which is spring constants by Hooke's law. All of these are positive. Okay, so here. Okay. And this is second order, which means that we need two initial conditions to find out particular solution, right? So y of 0 is y naught. Okay. And then y prime of 0 is v naught. Because y prime is what? Velocity, right? So v naught means initial velocity. That's the initial velocity. Okay. All right. And then we assume that there is the initial velocity right here. Sorry. Okay, here m. Okay. Now let me make this one to let me just rewrite this one as the simple equation as simple as possible. Okay. Let's say just consider ay dou prime plus by prime plus cy is equal to f. Okay. And then we assume that external force equals 0, so that this is going to be homogeneous, right? And definitely we assume the A is not equals. I mean, so A, B, C are positive. Okay. All right. Let's find a general solution. Okay. Before we just think about the before investigating particular solution by considering initial condition, we need to figure out the general solution first. Okay. So find general solution. Okay. So we just try to guess what does the solution look like. Something let's say y is, for example, y is a sine of t. Maybe y of t is something like the sine or cosine. Then we second derivative of sine plus first derivative of sine plus sine equals 0. Can you get to 0? I don't think so, because second derivative of sine is sine. Okay, but first derivative of sine is cosine. So sine, cosine, sine, sum of sine, cosine, sine equals 0. I don't think so. So what kind of functions we have to choose? I mean, y must be so that sum of these three terms turns out to be 0. So I think exponential function, because for example, y of t is e to the t, then y prime is e to the t, and then y second derivative is also e to the t, right? So if you just choose appropriate value for a, b, c, probably we can get 0, which means that there is a chance to become 0 when we set y as something e to the t, something involving e to the t. Okay, is that? So just guess, okay? Let's say y of t is equal to e to the rt. R is a real number. We don't know yet. Okay. And then we substitute this one into the differential equation. Okay. So then y prime of t is going to be r times e to the rt. And then y second derivative of t is going to be r squared e to the rt. So substituting these into the differential equations, then simplify them, then we'll get this a times r squared e to the rt, right? And then plus b times r times e to the rt, and then plus c times e to the rt is equal to 0. Okay, and because the e to the rt is a common factor, so factoring out e to the rt in left-hand side, so we're going to get e to the rt times ar squared plus br plus c is equal to 0. Oh, okay. Then see, e to the rt is what? You know what, since what here e to the rt is always positive, isn't it? For any r and t. For any but r is a real number, okay? And then t is represent time, right? It should be I think r and then plus including 0. What does that mean? Because the t represent time, right? Is there a negative time? No, minus 1 second, minus. There is no such a concept in time, right? Time must be the non-negative. That's the that symbol represent non-negative, which means that the set of all real number, okay? All real number, but say all real number, but t is greater than or equals 0. So plus means a positive, and then including 0. Plus means positive. Okay, so that means a non-negative. Yeah, so basically it means non-negative. Okay, that's mathematical expression of that non-negative. Okay, so e to the rt is greater than 0, right? Because you see, for what's the graph of e to the rt? This one or that one, right? So either way, e to the rt above the I mean, this is t-axis, right? T-axis, so positive. So okay, so since e to the rt greater than 0, that means what? That equation, left-hand side equals 0. That means that what? A times r squared plus b times r plus c equals 0. This is a quadratic equation, right? Okay. So we know the solution of that quadratic equation. R is what? R is equal to uh, minus b plus minus square root of b squared minus 4ac over 2a, is it? Okay. Now then what? So, which means that what? See, we got this one. 3 cases. Case 1, b squared minus 4ac, which let's say from here, let's say d is set with the b squared minus 4ac. So these means what? Discriminant, right? These means a discriminant. Okay. So if d is greater than 0, case 2, d equals 0, in a case 3, d is less than 0. So if d equals greater than 0, then it turns out that r is the real number, right? Which means that that quadratic equation has 2 distinct real roots. By the way, in that quadratic equation is called the characteristic equation. Characteristic equation. Or it's called the auxiliary equation. Simply saying the aux equation. Anyway, so d is greater than 0, which means that characteristic equation has 2 distinct roots. So let me just say Ox equation, okay? So Ox equation two distinct root, which means that what? That system, I mean, that differential equation has two distinct real solution, isn't it? Think about this. Okay. So give me a second. If d is greater than 0, okay, then let's say R is the I don't know what letter did I use. Give me a second. Then which means that yeah, R1, then R1 is gonna be minus B and then plus the square root D over 2A, and then other one, this is must be real number, right? Real number, and the R2 is going to be minus B minus square root D over 2A. This is also belong to real number. So means then Y, let me say Y sub 1 of T is e to the R1T must be solution, isn't it? Solution to that differential equation, isn't it? Why? Because, you know, the characteristic equation has a solution means that this differential equation has a solution. Why? Because when e to the RT satisfy, I mean that in that characteristic equation, if R satisfy that characteristic equation, then e to the RT must satisfy that differential equation. Okay, that's why e to the R1t must be solution to the differential equation, and y of t, y sub 2t defined by e to the R2t. Sorry, this is also solution. Okay, e to the R2t is also solution. So this one and by 2 or, but these are real value, right? So real solution. Okay. So if d is greater than 0, then differential equation has two distinct real solution. Case 2, if d equals 0, then that characteristic equation has only one real root, right? So y of t is equal to e to the just r t, where r is what? Just minus b over 2a. Because the d equals 0, then that square terms is gone. So we got just minus b over 2a. We got only one real root in the characteristic equation. So differential equation has only one real solution. Okay. So only one's case 3. D is greater less than 0. Then what? Then R is what? R1 is, you can say alpha plus the beta, and then R2 is alpha minus the beta I. Because if D is less than 0, then we're going to get complex root, right? Two distinct complex root. And then here alpha means the minus b over 2a. And then beta is what? The square root d over 2a, is it? Okay. So, and then y1 of d is the e to d r1t, right? This is equal to e to the alpha plus, alpha plus beta I t, and y2t is equal. Oh, okay, let me just simplify this. We got this one. That means e to the alpha t, right? And then times, right? E to the beta ti, isn't it? But by the Euler's formula, this is e to the alpha t. Euler's formula, e to the beta ti is what? Cosine beta t plus I sine beta t, isn't it? E to Euler formula, e to the well, a I is equal to cosine a plus I times sine a. That's a formula. That's Euler's formula. In a, okay, you see this one in an, I don't know, complex analysis course. Okay. 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 So, and then y2 t is equal to e to the r2t is equal to e to the alpha, the minus beta I t, right? So that is equal to e to the alpha t, and let me use bracket instead of parentheses because there are so many parentheses. Alpha t and then cosine, right? And then beta t, right? And then what? This is plus or minus? Why? I thought this is plus times I times sine minus beta t, isn't it? But that is equal to what? Minus. Why? Because sine is what? Yeah, exactly. This is odd function. Yeah. Odd function, odd function, even function, yeah, odd function. Yeah, exactly. Yeah. Okay. Okay. So we can talk about any, yeah. So we talk about this one. That spatial case three is little bit, we have to things more a little bit in case three. So we talk about case three later. Okay. So let's see case 1 and 2. Okay. So now okay, so I'm gonna hold the case three. Okay, I'm not gonna elaborate case three on detail at this moment. Okay, so we just see example. Okay, I don't want to get intimidated for case three. So let's see case 1. So I want to find out the solutions to this one, that differential equation. Y second derivative plus 5y prime plus 6y is equal to 0. Okay. Yeah, so step 1 is gonna be step 1 should be finding auxiliary equations. I mean characteristic equation. Okay, so the auxiliary equations is what? Just r squared, right? Plus 5 times r, right? Okay. And then plus 6, okay, is equal to 0. So now then this is going to be r plus 3, and then plus r plus 2. Okay, this is equal to 0. So r is a minus 2 and minus 3, right? So yeah, we got two, distinct real root. Thus, what? Y1 of t. So this is saying that y1 is e to the negative 2t, and y2 of t is equal to e to the negative 3t. And these are solutions. Okay. But I want to find out general solution, not just a solution or solutions. Okay. So here's a question. How can you find a general solution? Okay. So here's the answer. Yeah, we can construct the general solution from these two solutions. Actually, in examples, we already got the general solution. The general solution y of t is equal to c1 times y1, okay, y1 of t plus c2 times y2 of t. That's the general solution, actually. Because c1, c2 will be determined by initial conditions. Remember that in that differential equation, we got two initial conditions, right? So using that, these initial conditions, we can figure out C1 and C2. So this is a general solution actually. So so we can construct the infinite number of, depending on C1, C2, we're gonna get so many different solutions, right? From there. So that's why you can say this is initial conditions. Okay. So now then the y general solutions, y of t is gonna be C1 times y1 of t and that plus C2 times y2 of t. Okay, so you're yeah. C1, C2 is a real number. Okay, it's simple, right? But here's a problem. Did you catch a problem for finding a general solution if the form of general solution is like this? Look at the case 1, 2, 3. C1 is 0? It could be, depending on general solution. Yeah. If you set the general solution as C1 times y1 plus C2 times y2, which case we're gonna get problem? Yes, case 2. If d equals 0, we're gonna get only one solution, right? That's the problem, right? I mean, case 2, we got only one, solution, not pair of solutions. Then how can you find the general solution when case 2? That's the problem, right? So we'll talk about this one later too. So basically, idea is this: you're gonna find out another solution which is cannot be expressed as the y1, which means that when you multiply number by y1, you're gonna get the y2. The y2 cannot be the candidate. That one cannot be a candidate of y2, which means that I want to find out another solution which cannot be generated by y1. So we find out that kind of solution. So we put that one into here. That's going to be the general solution for case 2. That's a basic idea, but we'll talk about this one in other section. Yeah. So the next one, let's see. Okay. All right, so we see examples, integral problems. And step 1, I believe you did that, okay? So you complete that, I hope so. And there's a particular solution is this, okay? Please check by yourself, okay? We're gonna move to next step. So here's a question. All right, so we got the the form of general solution, C1 y1 plus C2 y2. So first one, but what if for example, y2 of t is simply identically 0 solution. I mean, either y1, y2 is simply 0 function, 0 solution. So we're gonna get problem. And then second one, so what if y2 t is a constant, a multiple of y1 t. Okay. So here's the answer. So first one. Answer for the question 1. Then what? C1y1 plus C2y2 must be C1y1. Right. So this one has only one constant C1, right? So it cannot be expected to satisfy two initial conditions. So example, C1, that's one, doesn't satisfy both initial conditions. I see. Okay. Here's the example. Let's say y1 is e to the t, and the y2 is 0. Okay. And initial conditions, y of 0 is 0, and then y prime of 0 is 1. Okay. You see that? Y of 0 is 0, then C1 must be 0, right? But y prime 0 is 1, then C1 must be what? 1. It's contradiction, right? The second one. So let's say this is the answer for the second question. So let's say y2 is equal to k times y1, which means that, k times C1 times, k times, k times C1 times y1. Oh, sorry, k times y1. Sorry. Okay, I just made a mistake. So C1 then what? C1, oh, my bad. C1 times y1 plus C2 times y2 is equal to C1 plus k times C2 times y1. Okay, but C1 plus k times C2 can be written as C. Okay, y1. This one has only one solution. So we're going to same problem as the first question. Example, y1 is e to the t, right? y2 is 2 times e to the t, which means that 2 times y1. And the initial conditions, let's say initial condition is given as y of 0 is 0, and then y prime 0 is 1. Okay, then we're going to get problems. So from there, we need the following concept. Here's definitions. This is the linear independence of two functions. Which is definition, a pair of functions, y1, okay? y1 of t and y2 of t. What does that mean? Two functions are linearly independent. Okay, this is y2 are linearly independent on a certain interval. Okay, on the interval I. Here, interval I means a certain domain of function. Okay, common area of the domain of y and y2. Okay, it means that means what neither of them is a constant multiple of the other one. multiple of the other, okay? On I, in over I, okay? So now then from based on this, we build up the theorems, representation of solution to invariant problems. Oh, sorry. So of solution to invariant problem. Okay, so now we can say that okay, and for the given invariant problems, ay dot prime plus by prime plus cy equals 0. And then y of t0 is equal to y0. And then y prime of t0 is equal to y1. So what's the general solution? The general solution must be a general solution. So y of t, it must be c1 times y1 plus c2 times y2. This is what we did before, right? But here's one more condition. Y1 and y2 must be linearly independent. Okay? So this given here, okay? And then y1, y2, right? If y1, y2 are solutions of this differential equation, and they are linearly independent, then this must be unique solution. That's the representation theorem of the invariant problem. Let me tell you, okay. So two solutions, y1, y2 are solutions of this differential equation. Okay, and then they are linearly independent. Then C1 y1 plus C2 y2 must be unique solution of that invariant problem. That's the representation of the solution to our invariant problem. Or you can say representation theorem. Okay. So then how can you know that two solutions are linearly independent? I'll tell you Wronskian. Okay. The Wronskian. This Wronskian is this. Y1 times y2 prime minus y1 prime y2 equals 0. If this is equal to 0, that holds at any at any t. Okay, this is a Wronskian. Okay, that's a Wronskian. If Wronskian is oh, give me a second. Sorry, give me a second. That's a Wronskian. Sorry, if Wronskian equals 0, okay, then y1 y2 must be linearly dependent. Okay. This is Wronskian. Then y1, y2 are linearly. Negative infinity. Okay. So normally, usually we is denoted by, I mean, this one denoted by W. Okay, W. If W equals 0, that means y1 times y2 are linearly dependent. Why? Because this is comes from, if you know about the linear algebra, this one comes from the determinant of y1, and then y2, and then y1 prime, y2 prime. Determinant of the 2 by 2 matrix, actually. You may say that, oh, I thought, matrix, entering the matrix must be number. No. In the matrix, every entry can be a function. Okay. So this comes from this. So the determinant is 0, then they are linearly dependent. Keep in mind that. Okay.